Hey y'all, welcome back. On tonight's homework, we are practicing some old AP test problems. So hopefully you're starting to become a little bit more familiar with the style of problems that you can expect to see on the AP test. And while some of these are going to require a calculator, not all of them, and to know whether or not you should be using a calculator, you're going to be looking for this Desmos logo. This, like I've said before, is the first year where you're going to be allowed to use Desmos on the calculator section. So we want to make sure that you're taking full advantage of that. Number one says the graph of the differentiable function f shown for x values between -6 and 7 has a horizontal tangent at x equals -2. So if x equals -2 is right here, that means this point has a horizontal tangent, and we can conclude then that because it's concave down at that point, that we have a relative or a local maximum there. And is linear for 0 to 7. So between 0 and 7, basically from here to here, we have a linear function. So we've got a constant rate of change. Let R be the region in the second quadrant, bounded by the graph of f, the vertical line x equals -6, and the x and y axes. In other words, the shaded region. So part A says the function g is defined by this function, the integral from 0 to x of f t dt. Find the values of g of -6, g of 4, and g of 6. So let's start with g of -6. g of -6 is going to be the integral from 0 to -6 of the function f. So we're just essentially finding the area underneath the curve between 0 and -6. Now, notice that the endpoints here are sort of out of order, right? Our lower bound is bigger than our upper bound. So if you want to fix that so that we don't have to worry about that later, we can negate this integral and swap those boundaries. So let's find the area underneath the curve from -6 to 0. That area is given. Region R has area 12. So this is just going to equal -12. The reason why it's negative is because we had to swap the sign there and change the bounds. So yeah, so just to be very clear here, g of -6 is -12. Now let's find g of 4. So 4 is going to be the integral from 0 to 4. Those boundaries are in the correct order, so we don't need to worry about changing the sign or anything. And so we're looking for the area between 0 and 4. That is going to be the area of this little triangle right here. Okay, it's got a base of 4, a height of 2, so it's going to be 1/2 times 4 times 2. 4 times 2 is 8, and half of 8 is 4. So g of 4 is 4. Finally, g of 6, we're going to calculate that very similarly. We've got not only the triangle that we just found, but then there's also this area under the curve between x equals 4 and x equals 6, right here, a little red triangle. And that area we're going to consider negative because it's below the x-axis. So this is going to be that the area on top 4 minus the area of this triangle, which is going to be 1/2 times the height, which is 1, times the base, which is 2. So half of 2 is 1, so 4 minus 1 is 3. Part B says for the function g that we defined in part A, find all values of x in the interval at which the graph of g has a critical point. So a critical point is one where the derivative, so where g prime equals 0 or undefined. Okay, so let's define g prime. So g is given as the integral from 0 to x, f of t dt. So if we want to differentiate that and find g prime, we're going to differentiate this integral. So we're just going to substitute in that upper bound x into t, and then multiply by the derivative of x, which is just 1. So this is just going to be f of x. So it's just the graph that we see above. So if we want to find a point between 0 and 6 where this function is either 0 or undefined, we don't see any holes or vertical asymptotes or any gaps in the graph So it's never going to be undefined, but it is equal to 0 right here, okay? So it's going to equal 4. So how do we want to write this? It's got a critical point. So the only critical point and that is where G prime equals 0 is at X equals 4. Letter C says the function h is defined as the integral of f prime. Find the values of h6, h prime 6, and h double prime 6. So I guess since we have to find h prime and h double prime, let's just go ahead and do that first. So I'm going to just rewrite h of x. Now I'm going to write h prime, which is going to be the derivative of that integral. So if I substitute an x, it's going to give me f prime x. And then so h double prime, oops. Where's my undo button? There it is. Is going to be f double prime. Okay, so let's see here. Where were we? So yeah, h is really just f of x. Well, let's see here. Be f of x actually minus f of 0. So f of x minus f of 0 is going to be f of x. Let's see here. If I substitute in 0, it's going to be 2. So minus 2. Okay, so now that we've defined all these functions, we can go ahead and calculate h of 6, h prime of 6, and h double prime of 6. So h of 6 would be f of 6 minus 2. So f of 6 is negative 1. Negative 1 minus 2 is negative 3. H prime of 6 would be f prime of 6. So it's the slope of the curve when x is 6. I'm going to erase some of this. Now, where x is 6, and all along that part of the curve is linear. So we could just do a basic rise over run here to find the slope. So like just from here to here, if we're just looking at here, we're going down 1 over 2. So the slope is negative 1/2. And then h double prime of 6 is going to be the slope of the rate of change of the rate of change. And the rate of change of f is constant. Okay, it's always negative 1/2. So the derivative of negative 1/2 is just always going to be 0. All right, and that is enough for that one. Number 2 says, given the function f of x equals, and then we've got an integrable function, determine all x values for any for which f has a point of inflection. So that is when f double prime changes sign. So we're going to have to find f double prime. We're going to have to create a number line or a sign chart and basically keep track of when f double prime is positive and when it's negative. And if it ever changes sign, that point will be a point of inflection. So f of x is defined. So let's just write what would f prime be, and that's going to be the derivative of all this. So substituting in x into t gives me x to the 5th plus 10x to the 4th. And normally, if that's the upper bound were anything more than just an x, then you'd have to multiply by the derivative of that. And technically, we do that here, but the derivative of x is just 1. So we want to find the second derivative, and we can use the power rule to do that. So that's going to be 5x to the 4th plus 40x cubed. And in order to make this sign chart, we're going to need to know where x is 0. So we're going to solve this equation. So we're going to solve this equation to find these subcritical points for our sign chart. Let's see, what can we factor out here? We can factor out a 5x cubed, and that would leave me with x plus 8. So we're going to have two subcritical points, one at 0 and one at -8. Now, neither one of these has an even multiplicity. The 0 has a multiplicity of 3, but what we want to be thinking about is if you do end up with a 0 or a critical point that has a multiplicity that's even, like let's say it's like x squared or something like that, then you will expect there to be no sign change there. So I'm expecting there to be a sign change at 0, -8. So I'm assuming you're going to have 2 points of inflection, but we do want to double check that. So, just in case we made a mistake somewhere. So I'm going to put 0, I'm going to put -8 here. We're going to have a total of 3 intervals. And if I substitute in a number like, let's say, -10, I get a negative times a negative, which is positive. If I substitute a number like -1, I'll have a negative times a positive, which is negative. And if I substitute a number like 1, I'll have a positive times a positive, which is positive. So just like we suspected there to be a sign change at each subcritical point, we do that did play out the way we thought it would. So we've got 2 points of inflections. So our 2 points of inflection are going to be at x equals -8 and x equals 0. Our justification is because f double prime changed signs. Number 3 says consider the curve shown given by the equation 6xy equals 2 plus y cubed. So we have an implicitly defined function here. And so when we go to find dy dx, basically what we're going to do is differentiate both sides with respect to x. So in other words, we're going to differentiate 6xy, and we're going to differentiate 2 plus y cubed. Both of those we're differentiating with respect to x. So for the first one, we're going to have to use the product rule. So the derivative, so in our two functions here will be 6x and y. Derivative of 6x is just 6. So you have 6 times y plus 6x times the derivative of y with respect to x. That's our dy dx. Equals, the derivative of 2 with respect to x is just 0. And the derivative of y cubed with respect to x is just 0. So, sorry, that's not going to be 0. What am I thinking? That's going to be 3y squared, we're using the chain rule, times dy dx. So now we're trying to isolate dy dx. So I'm going to bring my dy dx's to one side and everything else to the other side. And really the only other thing is this 6y. So I've got 6x dy dx plus 3y squared dy dx equals negative 6y. And so now if I factor out the dy dx, I'm going to have dy dx times 6x plus 3y squared equals negative 6y. And I could divide both sides by the 6x plus 3y squared. I'm kind of running out of room here, so let me move all this over a little bit. So dy dx is going to equal negative 6y over 6x plus 3y squared. And I just realized that I made a little mistake here. When I move the 3, this term over here, when I move that to the left-hand side, I should have subtracted that from both sides. So let's fix that. This should be a minus here, and which means this is minus here, and which means this is minus here. Now, the whole goal here is to prove that, or show that dy dx equals 2y over y squared minus 2x. And you might look at this and think, well, that doesn't really look the same. But if you look a little closer, you can see that there is a common factor that we can divide both the numerator and the denominator by to simplify this fraction a little bit. And that is 3. We could divide both of these by 3. So this would equal negative 2y over 2x minus y squared, and it still doesn't really, it's very close to what we have over there. It's still not quite the same. what we need to do is multiply both the numerator and the denominator by -1. So dy dx is going to equal, if I multiply the numerator by -1, it'll just be 2y. And if I multiply the denominator by -1, I get y squared minus 2x. So there you go. Part B says, find the coordinates of a point on the curve at which the line tangent to the curve is horizontal. So if the line tangent to the curve is horizontal, then that means y prime must be 0, right, if we have that horizontal tangent line. Or explain why no such point exists. So if y prime needs to be equal to 0, another way of saying that is that dy dx must be 0. And dy dx was defined in part A. So if dy dx must be 0, then that means that 2y over y squared minus 2x must be 0. In order for that horizontal tangent line to, in order for there to be a line that is tangent to the curve and that line is horizontal. So in order for this fraction to equal 0, the numerator has to equal 0, because 0 divided by anything is going to be 0. Another way to get there algebraically is just to multiply both sides by y squared minus 2x. So if 2y must be 0, then y must be 0. And so we have the coordinate, if there is one, or at least the y coordinate, but we still need the x coordinate. So to get the x coordinate, we're going to plug in this y back into the original equation. So 6 times x times 0 equals 2 plus 0 cubed. Now, this is actually going to simplify. 0 times anything is 0, so this left-hand side is 0, and the right-hand side is just 2. And we get 0 equals 2, which is obviously a false statement. So whenever you get no solution here, that means there is no solution, meaning there is no x coordinate where y is 0. So in this case, we're just going to say there's no point that has a horizontal tangent line. So how do we want to say that? We want to say there, since no, well, how do I want to say this? There's no point on the curve when y equals 0. Therefore, there is no point at which the tangent line is horizontal. All right, part C says, find the coordinates of a point on the curve at which the line tangent to the curve is vertical. Okay, so if on the curve you've got like some vertical tangent line, that means the slope of that line or that curve at that point must be undefined. A vertical line has no slope. So in order for that dy dx to be undefined, and actually we don't want to say equals undefined because undefined is not really a number that it can equal, but in order for this to be true, then the denominator of that fraction needs to be 0. So y squared minus 2x must be 0. So essentially what I have here is a system of equations. I've got this equation and I've got the original equation, 6xy equals 2 plus y cubed. I think the best way to approach this is going to be using the substitution method. And the easiest variable to substitute for here, or to isolate rather, is this going to be this x. So I'm going to rewrite this equation as y squared equals 2x. And divide both sides by 2, or multiply both sides by 1/2. And use this expression for x right here in the other equation of the system. So 6 times 1/2 y squared times y equals 2 plus y cubed, and hopefully we can solve this for y. This looks like a pretty terrible equation, but let's see here. So this would be 3y cubed equals 2 plus y cubed. So 3y cubed minus y cubed is going to be 2y cubed equals 2. Divide both sides by 2. And so we get y cubed is 1. And so y must be 1. So if y is 1, we can now go back and solve for x. Probably the easiest place to do that is going to be in this equation right here because the x has already been isolated. So 1/2 times 1 squared is x. 1 squared is 1 times 1/2 is 1/2. So x is 1/2. So this one we actually do have a coordinate. 1/2, comma 1. Number 4 says, given the equation g of x, and g of x is this combination of 3x squared and this integrable function sine t, determine g of 2. So we're just going to substitute 2 in everywhere we see x. Not where we see t, so be careful with that, just where we see x. So g of 2 is going to be 3 times 2 squared plus the integral from 2 to 2 sine t. Now, luckily here, we're not going to have to actually find the antiderivative of sine, although that shouldn't be too much trouble, because if we integrate any function from a number to itself, when these two endpoints are the same, that integral is just going to equal 0, because there's going to be no area under a curve if the partitions are overlapping like that. So this is just going to be 4 times 3 is 12, plus 0 just equals 12. So g of 2 is 12. Part B wants g of 0. So similar setup here. G of 0 is going to be 3 times 0 squared plus the integral from 2 to 0 sine t. And so now we need to write down the antiderivative of sine. Now the derivative of sine of cosine is negative sine, so the antiderivative of sine is going to be negative cosine. So g of 0 is going to be negative cosine from 2 to 0. Now notice that the endpoints on that integral are backwards, right? 2 is the bigger number. But that's actually we're not going to worry about trying to flip those in this case because the fundamental theorem will just sort of take care of this for us. So this is just going to be negative cosine of 0 minus negative, so I guess plus, cosine of 2. Since cosine of 0 is 1, we can rewrite this as cosine of 2 plus 1. Or not plus 1, minus 1. Oops. Letter C says determine the derivative of g. So we're going to differentiate, go back to this original function, and we can differentiate both of these pieces separately. We can differentiate 3x squared first using the power rule. So that would be 6x. And then differentiating this piece is going to give us just sine x. And that's I don't think there's anything else we can do to simplify that. Now, if we want to evaluate that derivative at pi over 4, we just need to substitute in pi over 4 into x. So 6 times pi over 4 plus sine of pi over 4 will be 6 divided by 2 is going to be 3, so 3 pi over 2 plus, and then sine of pi over 4 is root 2 over 2. So that's a good answer. We can simplify it a little bit. We can bring these two fractions together, but you don't really need to. I'm happy with this answer. You could, if this was a multiple choice question, they might write it like this, where they add the two fractions and combine them into one fraction, but that's not going to be a required step on a free response. g double prime of x. Well, we just need to go ahead and differentiate this function up here one more time. So g double prime of x is going to be 6 plus cosine x, and that's all I need to do there. F wants g double prime of pi, so we're just going to substitute in pi for x in that equation we just wrote. Cosine of pi is -1, so we have 6 plus -1, which would be 5. All right, whew, that was kind of a long sheet there. Number 5, okay, so now we're starting to use Desmos here. The derivative of a function f is defined by f prime here. If f of -1 is 8, find f of 6. So this is going to be another one of those fundamental theorem of calculus problems. And we'll set up our definite integral like this, the integral of f prime dx from a to b, and in this case we want to use -1 and 6, is equal to f of 6 minus f of -1. And if we're trying to find the value of f of 6, we're going to isolate that by adding f of -1 to both sides. So this is what we're going to type into the calculator. To get f of 6, we want the integral, and I'm not just going to type f prime here, I'm just going to type out the entire function. From -1 to 6, x squared minus 4x minus sine of 2x. Make sure that that whole entire expression is in parentheses and with a dx at the end. You'll get an error if you forget that set of parentheses. So we have that, and then we want to add f of -1, which is defined right here as 8. So this is what we're going to put in the calculator. So let's open up Desmos here and start typing away. So the integral from -1 to 6 of, not f, we're going to actually type out the whole equation here, x squared minus 4x minus sine of 2x, close that set of parentheses, dx. And so that evaluates the area under the curve from -1 to 6, and we want to add 8. So f of 6 is going to be approximately equal to 10.963. And there's no units here or anything, so we're just going to leave it just like that. Number 6 says the velocity of a particle is defined by v of t equals t cubed minus 3 times cosine of t plus 2. If the position when t is -3 or is 5, find the value of p of 4 to the nearest thousandth. So another fundamental theorem problem here, the integral of vt from -3 to 4 is equal to, now velocity is the derivative of position. So this is going to equal to position at 4, position is the antiderivative of velocity, minus the position at -3. So if we're looking for p of 4, we're going to isolate that by adding p of -3 to both sides. So we've got the integral from -3 to 4 of t cubed minus 3 times cosine of t plus 2, all of that times, or dt, I should say, not times, plus p of -3, which is 5. So once again, this is what we're going to put into the calculator. So back on over to Desmos. We can clear this out. There we go. And say the integral from -3 to 4. Just type this out. Don't use the brackets. I think you're just going to have to stick with parentheses on Desmos. I think it's going to expect something different with brackets. You can experiment with that, but I've just find that it's a little safer to do the parentheses. And then we got that dt, and then plus 5. And so we get 13.544. And any units here? We are talking about a position, but yeah, no units are given, so we're just going to leave it like that. Okay, number 7 does not need a calculator, neither does number 8, so we'll put this away for now. It says the function f is shown if g is the function defined by g of x equals the integral from 9 to x. What is the value of g of 8? So g of 8 is the integral from 9 to 8 of f of t dt. Okay, so I definitely noticed some people kind of getting confused. We've been talking about integrals and the fundamental theorem a lot, but don't lose track of the fact that this is just talking about an area. Okay, so if you've got the graph here, you don't need to go through and like find the equations of each line and construct a piecewise function as an equation or anything. You're just going to find the area from 9 to 8. Now, that's going to be this area here. But if we're going to look at these boundaries a little bit more closely, this is going to also be equal to the opposite of the integral from 8 to 9. So let's flip those so we get the correct answer here. Now the area here is 1 times 2 divided by 2, so half base times height, which is just 1. Because it's below the x-axis, we're going to be considering this negative 1. Okay, but because the boundaries were backwards, we get a minus negative 1, which is actually going to end up being positive 1. So kind of weird and kind of annoying. Got to keep track of all those negatives, but just be careful on a problem like that. Number 8, it says the graph of f prime, which is the derivative of f, is shown. If f of 0 is 3, what's the value of f of 9? We're seeing a lot of these kind of problems where I give you one coordinate and I'm asking for the y coordinate of some other x value. And a lot of times, like what we saw like on 5 and 6, we're also given or we're expected to know that we need to set up a version of the fundamental theorem. And so that's going to be the case here as well. The integral from 0 to 9, f prime x dx is equal to f of 9 minus f of 0. And again, we're solving for f of 9 here. So we're going to add f of 0 to both sides. Don't forget, just like on number 7, this is talking about the area between 0 and 9. We don't need to flip the boundaries, though, because they're in the correct order. So from 0 to 9 is going to be from here to here. So we have a triangle here that has a base of 6, a height of 2, 1/2 times 6 times 2. 12 divided by 2 is 6. So this area, this has an area 6, but it's we're going to think of it as negative 6 because it's below the x-axis. The next triangle has a base of 3 and a height of 2. 3 times 2 is 6, divided by 2 is 3. So that area is we're going to think of that as positive 3. So the overall area from 0 to 9 is negative 3. And maybe I'll just rewrite this equation with that thrown in there. Negative 3 equals f of 9. And f of 0 is given. It's 3, so minus 3. We can add 3 to both sides to conclude that f of 9 must be 0. Number 9, it says if g is the an antiderivative of f such that g of 9 is negative 4, what's the value of g of 1? Okay, so we get yet another one of these kind of problems where the integral from 9 to 1, f of x dx, is since g is an antiderivative of f, that means that g prime is f. So yeah, the integral from 9 to 1 of f of x dx is g of 1, because g is the antiderivative of f, minus g of 9. So this area, which is a backwards area, right? So it's going to be the opposite of whatever we would normally get. From 1 to 9, let's see here. We got 1, 2, 3, 4, 5, 6 times 6 is 36. Divided by 2 is 18. So this area we're thinking of as negative 18 for that lower triangle. Now for this triangle right here from 7 to 9, the base is 2, the height is 4, 2 times 4 is 8, divided by 2 is 4. So the area here would normally be negative 14, but because those boundaries are backwards, it would be the opposite of negative 14, so it's going to be positive 14. And that's going to equal g of 1 minus g of 9. G of 9 is negative 4, so just g of 1 plus 4 will do. Subtracting 4 from both sides is going to give us g of 1, which is 10. Number 10 says the derivative of the function f is continuous on the closed interval 0 to 4. Values for f and f prime for selected values are given in the table below. If the integral from 0 to 4 of f prime is 8, then what is f of 4? Okay, so I think what this is sort of leading us to, if we've worked a bunch of problems like this in a row, looking at those boundaries of the integral, if I want to set up a fundamental theorem equation, I'm also going to need to reference f of 0, because the integral from 0 to 4 of f prime t dt is going to equal f of 4 minus f of 0. So if that integral equals 8, like it says in the problem, that means 8 is equal to f of 4 minus f of 0, which in the table is given as 5. If I add 5 to both sides, I'm going to get f of 4 equals 13. So the correct answer here is E. Number 11 says, given the graph of f below, determine each of the following. Show the work that leads to your answer. A says, what is the average value of f on the interval negative 6 to 5? So to find the average value, we're going to do the integral from negative 6 to 5 of function f, so f of x dx, divided by the interval length, which is going to be 5 minus negative 6, so that'd be 5 plus 6. We'll be dividing by 11. So what it looks like what we need to do now is find the area between negative 6 and 5. So here's where x is negative 6, 5 is 1, 2, 3, 4, 5. Okay, so we're going to get the entire area here. So this first triangle over here to the left has a base of 1, 2, 3, 4, a height of 2. 4 times 2 is 8, divided by 2 is 4. Then we've got a little semicircle down here, which would be half times our circle formula pi r squared. So if the radius from the center to the circumference is 2, 2 squared times a half, that'd be 4, divided by 2 is 2. So this is going to be 2 pi, but since it's below the x-axis, we're going to call it negative 2 pi. The last shape, which is a triangle, has a base of 3 and a height of 2. 3 times 2 is 6. 6 divided by 2 is 3. Okay, so that means that this numerator up here, which is what we're trying to calculate there, is going to be 4 plus 3, which is 7 minus 2 pi divided by 11. I don't think there's anything we can do to simplify that further. B says if g of x equals the integral from negative 6 to x, find g of 2. So if we're finding g of 2, we're going to find the integral from negative 6 to 2, which just means the area from negative 6 to 2. So it's going to be all the area except for that last triangle over to the right. So g of 2 is just going to equal 4 minus 2 pi, just that, and we can't really simplify that, so that's going to be our answer. Letter C says if h is the integral from negative 2 to x squared, f of x dt, find h prime 2. So first let's just find h prime, which is going to require us to substitute in this x squared into t. So that'd be f of x squared. But then we have to multiply by the derivative of x squared, which would be 2x. So if I want h prime of 2, I'm going to substitute in 2 everywhere where I see x. So that'd be f of 2 squared is 4 times 2 times 2 is 4. Now f of 4, I'm going to need to look back at the graph to figure out what that equals. Let me erase a little bit of this, get some of the messiness out there. So f of 4 is going to be the y value at 4, 1, 2, 3, 4. So it's going to be the y value right here, which is 1. So that's going to be 1 times 4, which is 4. Letter D says if w equals 3x squared plus the integral of negative 2 to x of f of t dt, find the second derivative. So let's first find the first derivative. The first derivative of 3x squared, using the power rule, is going to be 6x. And then finding the derivative of this piece is going to require us to take that x, that upper bound, and plug it into t. And we would multiply by the derivative of that upper bound, but the derivative of x is 1, so we're just going to kind of not really worry about that too much. So plus f of x. Okay, so that's w prime, but now we want w double prime of f of 4. Jeez, it's kind of hard to say. W double prime. Sounds like a wrestling organization. Okay, so w double prime of x is going to be the second derivative of this. It's going to be the derivative of the first derivative. So the derivative of 6x is x. The derivative of f of x is just f prime. So if I want w double prime of x, of negative 4, I'm going to substitute in negative 4 everywhere I see x. That'll be 6 plus f prime of negative 4. And that f prime of negative 4 is really talking about the slope of that graph when x is negative 4. So x is negative 4, 1, 2, 3, 4 right here. So the slope of that line segment is going to be equal to f prime of negative 4. And it looks like it's going down 1 over 2, which means that that slope is going to be negative 1/2. So we have 6 plus negative 1/2, so 6 minus 1/2 is going to be 5.5. All right, number 12. 12 is just a straightforward integral problem. Yeah, just classic fundamental theorem here, where we can find the antiderivative of 2x cubed plus 3, and then substitute in 2, substitute in 0, subtract, and we should have our answer. So the antiderivatives of 2x cubed plus 3 is going to be, 2 divided by 4 is going to be 1/2, x to the 4th plus 3x plus c from 0 to 2. And let's see, if we substitute in 2 to the 4th power, let me count here, 2, 4, 8, 16. Half of 16 is 8, plus 3 times 2 is 6. The c's are going to cancel each other out. If I substitute in 0, I'm going to get 0 plus 0, so that's just going to be 0. So 8 and 6 is 14. So our answer here is C. Number 13 and 14. We got back-to-back calculator problems here. If f is the antiderivative of x squared over 1 plus x to the 5th, such that f of 1 is 5, then what is f of 4? So here we have got yet another one of these fundamental theorem questions, and just kind of looking forward to number 13 or 14. It looks like that's going to be set up very similarly. So f is the antiderivative of whatever this is. Now, when we go to type that in, we're going to have to give it a name. So I'm just going to say let g be the antiderivative of f. And so g will be x squared over 1 plus x to the fifth. And so if g is the antiderivative of f, that means that g prime is f. So when we set up that fundamental theorem, we can think of it like this. The integral of 1 to 4 of g, which is x squared over 1 plus x to the fifth, dx, is going to equal f of 4 minus f of 1. So if we're trying to solve for f of 4, we're going to add f of 1 to both sides. F of 1 is 5, so that means f of 4 is equal to 5 plus the integral from 1 to 4 of x squared over 1 plus x to the fifth dx. Now, this expression is not something you're going to be expected to be able to integrate by hand. So don't even, if you're like wondering, how would I even find the antiderivative there? Don't worry about that quite yet. So this is what we're going to type into the calculator. So let me pull that up. And let's get typing here. 5 plus the integral from 1 to 4 of x squared over 1 plus x to the fifth dx. And there you go. So we get f of 4 is approximately 5.375. Number 14 is going to be solved very similarly. So we're going to set this up with a fundamental theorem equation again. So the integral from 1 to 9 of the natural log of x cubed over x dx is equal to f of 9 minus f of 1. So here we're trying to solve for f of 9. So just like in the last problem and in several of the problems that we've seen so far on this assignment, we're going to isolate that by adding the f of 1 over to the other side. So f of 9 is equal to the integral from 1 to 9 of natural log x over cubed over x dx plus that f of 1, which in this case is 3. And I think I'm going to add that 3 on the front end here so it doesn't look like that it's part of the integral. Oh, come on, Mr. Schuler. There we go. 3 plus. Okay, so yeah, that's what we're going to type in. So I'm going to delete all this and just start from scratch here. 3 plus the integral from 1 to 9 of the natural log of x, all that cubed divided by x dx. And yep, f of 9 is 8.826. Looking at our answer choices, it does appear that they rounded versus truncating. I'm fine with that. The AP test graders will be fine with truncating, so don't worry about that little discrepancy there. You're not going to have two answer choices that are within 1,000th of each other. Okay, number 15. We do not need Desmos for this. It says the graph of f is shown on the figure below. If the integral from 1 to 3, f of x dx is 2.3, and f prime of x equals f of x, then what does f of 3, capital F of 3, minus f of 0 equal? Well, since the derivative of capital F is little f, then that means that capital F is the antiderivative of little f. So the integral from 1 to 3 of little f of x dx is equal to its antiderivative at 3 minus its antiderivative at 1. So the antiderivative is capital F. So that'd be the capital F of 3 minus capital F of 0. That means this expression, which is what it's asking for, is going to be equal to this, right? Which is the area under the curve. And actually, that number is given, isn't it? Right? It's just 2.3. Number 15 says the graph of f is shown in the figure below. If the integral from 1 to 3 f of x dx is 2.3 and capital F prime equals f of x. Okay, so just to be clear, what this means is that capital F is the antiderivative of f, little f. Then capital F of 3 minus capital F of 0 equals what? So it looks like we want to at least be thinking about the fundamental theorem again and setting up an equation. But you might notice there's a little bit of an issue here because the lower bound on this integral is 1. But this is looking for f of 3 minus f of 0. So let's take a look at that graph and see. All right, so basically what this is saying is that the area from 1 to 3 would be like from here to here. So that area is 2.3. And what we want is an equation for the area between 0 and 3 because we're looking for f of 3 minus f of 0. So if I were to write that integral from 0 to 3, f of x dx, that would equal capital F of 3 minus f of 0. And so, yeah, capital F of 3 minus capital F of 0 is going to be the total area under this curve. And so, like you can see, like if part of it's 2.3, the other part is just going to be like this extra 2 units. So this integral is going to be that 2.3 plus 2. Another way to kind of write this out would be to split this up and say, all right, well, if I want the integral from 0 to 3, I can find the integral from 0 to 1, which would be this area in here, plus the area from 1 to 3, which I can't really get from the graph because it's curved, but they do give us that it's 2.3. So this would be that those 2 units plus the 2.3, and that's going to give me my f of 3 minus f of 0. So the answer is going to be 4.3. Number 16, let f be a function defined on the closed interval between -3 and 4. Okay, so -3 here, 4, so the whole thing that we see here. And f of 0 equals 3. Okay, the graph of f prime, the derivative of f can, okay, oh yeah, so just let's make sure that we're clear here. This is the graph of f prime, not of f. And it consists of a line segment and a semicircle. And what intervals, if any, is f increasing? So in order for f to be increasing, that means the slope has got to be positive, meaning f prime has to be positive. So if we're looking at the graph of f prime, the only place where we see that it's positive is right up here. So that's between -3 and 0. So the intervals for which f is increasing is going to be from -3 to -2, and that's because f prime is positive. Okay, so the justification is that statement right here. And really the justification is just making sure that you understand and you're being clear about how you know that that's the answer. And you're interpreting that statement, f increasing. And then it says find f of 4. Show the work that leads to your answer. So I think we're going to have to set up a little, again, a fundamental theorem problem because they give us f of 0 equals 3, and we're interested in f of 4. So usually that's kind of your clue that, hey, we're going to set up a fundamental theorem problem. So the integral from 0 to 4 of f prime x dx is equal to f of 4 minus f of 0. So f of 4, which is what I'm looking for, is going to equal the area between 0 and 4 of f prime, which is what we see in the picture, plus f of 0, when f of 0 is 3. So f of 0 plus that area from 0 to 4 is going to give us our answer. So f of 0 is 3, and let's start looking at the area. So we've got this little positive triangle here, got a negative triangle here, and we've got like this kind of weird area. So we'll talk about that separately. So that left triangle has a base of 1 and a height of 1. So this is just going to be 1/2. This area has a base of 2, height of 2. 2 times 2 is 4, divided by 2 is 2. So we're thinking of this area as being -2. So far, the area from 0 to 4, we've got 1/2 minus 2. And then we've got this other kind of strange area going on here. So to figure out this sort of this extra negative area, let's think about how we would find the area of a square, but just the area that's not being covered up by the circle. So in other words, like all this area. Okay, we want like the area of the frame. And so when you're trying to find the area of the square that's not being covered up by the circle, we could find the area of the square, like the bigger shape. What's going on here? Find the area of the bigger shape and then subtract away sort of the whole, like what you're cutting away. So the same thing's going to be true here, where we can think of this as like a rectangle. Find the area of this rectangle right here, right? And that rectangle is going to be a 4x2 rectangle, so that overall rectangle is going to be 8. And then take away the area of the semicircle. So this is going to be 8 minus half of pi r squared, where the radius is 2. So 2 squared is 4, divided by 2 is 2, so it'd be 8 minus 2 pi. So since that area is below this area right here and here, all that's below the x-axis, we're going to subtract that whole expression. So minus 8 minus 2 pi. Okay, so f of 4 is going to be 3 minus 2 is 1, 1.5. Let me combine that minus 8 first. Let's see. It's too late to be doing fraction arithmetic in my head. Okay, so 3 minus 8 is -5. Minus 2 is -7. Plus 1/2 is -6.5. So -6.5 minus a -2 pi would end up being plus 2 pi. And yeah, that's the value of f of 4. All right, so it looks like we got 3 problems left, and they're all going to require the calculator. Number 17 says, insects destroyed a crop at the rate of this expression, tons per day. So that's a rate function where time is measured in days. To the nearest ton, how many tons did the insects destroy during the time interval? So this is a net change problem. We're looking for the net change in the number of tons that the insects destroy, the number of tons that the insects destroyed on that interval. So we want to find the integral from 7 to 14 of this rate function. I can't even read it because I wrote right over it. And let's bring this down a little bit. Okay, and that's going to be dt. And yeah, that's pretty much it. We just need to go ahead and type that in. So let's pull up Desmos. The integral from 7 to 14 of 100 times Euler's number to the power of negative 0.1t. All that over 2 minus e to the negative 3t. Yep, that's it. There we go, dt. And so that's going to be 124.994, which if you round it to the nearest whole ton, is going to be choice D, 125. Number 18, an object traveling in a straight line has position x at time t. If the initial position is x of 0 equals 2 and the velocity of the object is given as v, what's the position at time 3? So we've got another fundamental theorem problem, an integral from 0 to 3, okay, 0 to 3 of vt dt is going to equal the position at time 3 minus the position at time 0. So this is the net change. The last problem we were calculating a net change too, but we just use a calculator to do it. Here we're trying to, this expression is a net change. We're going to use the calculator to find that, but then we can use the fundamental theorem and use our understanding that the position at time 0 is 2 to find p of 3. And actually, I'm going to rename that because the position function actually has a name in this problem. I usually just kind of default to using p, but it's actually defined here as x. Okay, now this is a multiple choice question, so you don't have to worry about all the little details, but it's worth noting here that the derivative of x is v. And if it were a free response question, you definitely want to make sure to write that. Okay, so x of 3, which is what we're looking for, the position at time 3, is equal to the integral of 0 to 3. And since this is a calculator problem, I'm going to write out exactly what we're going to type in the calculator, which instead of being vt, will just be that function, the cube root of 1 plus t squared dt. And then we need to add the initial position, which is 2. Okay, so this is what we're going to put in the calculator here. So we have the initial position plus the net change, and that's going to give us our final position at time 3. So the integral from 0 to 3 of the cube root. Now, probably the easiest way to type this without finding this buried in the function menu is just to write 1 plus t squared and then raise that to the 1/3 power, which would be the same thing as cube rooting it. That's essentially what cube rooting actually means. So dt plus 2 is going to give me 6.511, which they are going to round up to 512. Our answer is D. All right, we've got one last problem here. If f prime is the square root of 1 plus 2x cubed and f of 2 is 0.4, then f of 5 is equal to what? Now, this homework has been like, gotta be at least half of the problems are this essentially the same problem, which is this fundamental theorem problem. So hopefully by now you've worked out enough of these to where you kind of know where the problem's going before you even get started. This is going to be our setup, but you guys should already know that. So we've got what we're looking for, which is f of 5. So f of 5 is equal to f of 2 plus the integral from 2 to 5 f prime x dx. So what I'm actually going to type in the calculator here is going to be f of 2, which is 0.4, plus the integral from 2 to 5 of the square root of 1 plus 2x cubed dx. And let's go ahead and type that in. So 0.4 plus the integral from 2 to 5 of the square root of 1 plus 2x cubed, and then right outside that square root we got a dt or dx, And yeah, there we go. F of 5 is 29.005. A. So that was kind of a long assignment. That took a little bit longer than I anticipated. I think maybe in the future we cut out some of those fundamental theorem questions, because I think after about the fifth or sixth one, it just kind of gets tedious. But hopefully it wasn't too bad for you. I hope you feel like you understand that fundamental theorem a lot better than when you started this assignment. So if you have any further questions or just want me to go into a little bit more detail on any of these questions, just please let me know, and I'll be happy to do that. Otherwise, y'all have a great evening, and I'll see you next time.